In this lesson, we're going to talk about algebra of functions. That means what kind of operations we can perform using functions. Well, we can add them, we can subtract them, we can multiply functions, we can divide functions, we can also compose functions. So first, let's see how do we define a sum or a difference or a product of two functions f and g when f has domain df and g has its domain dg. Well, look at these particular two functions. Let the blue one be called f and the red one g. So the domain of f is from 3 up to 10, and the domain of g is from 0 up to 9. Therefore, as long as we are in a common domain from 3 to 9, the yellow interval, then we can define the sum, the difference, or a product of two functions as a new function in such a way that the value of the new function at the point x is the same as the sum, difference, or product of values of each function separately. So if we look at the addition, how do we see the sum on this diagram? Well, at the point 3, the sum function f plus g will have a value 1 plus 2, so it will have a value 3. At the point 4, this is approximately 1.8 and another 1.8 because it looks like they are equal. So this will be about 3.6, somewhere here. At 5, we have a value 1 plus 3, so we're just adding these two values and we end up with 4 for the sum function. At 6, that will be 0 plus whatever it was before, about 3.5, the same point. At 7, negative 1 plus 4, so it will become 3. At 8, 0 plus 3, which is still 3. And at 9, 1 plus 2 is 3. So if we try to connect these points smoothly, the function looks somehow like that. So this purple graph is the graph of the function f plus g, a new function of x, and it's done by adding values of f and g by coordinates f of x and g of x. Similarly, the difference function and product function is defined by the difference or product of the values of particular functions. The quotient function is defined in similar way. However, we need to remember that as soon as g of x is equal to 0, such a function is not defined because we can't divide by 0. So the domain of f by g, it won't be just the intersection of the two domains, but also we need to remember to get rid of any points for which the denominator function equals to 0. So any roots of g function will have to be excluded from the domain. Therefore, the domain of sum, difference, and product of two functions is the same as intersection of the domains of the two functions. However, the domain of the quotient of two functions is the intersection of the two domains diminished by the set of zeros for the denominator. So we need to exclude the x values such that g of x, the bottom function, will be 0. So for example, domain of the quotient function f divided by g is the intersection of the two domains, which is interval from 3 to 9. However, we need to get rid of points 6 and 8. Here we have some exercises so we can practice our understanding of this notation. Given two functions, f of x, which is a linear function, and g of x, which is this quadratic function, find the following functions and their domains. So f plus g of x, that's a new function. It's a function that comes from f of x added to g of x, which is the same as just simply add x plus 2 plus x squared minus 4. That's a quadratic polynomial. Let's simplify it and leave in that form. Now, what's the domain of my new function f plus g? Well, the domain of it is the intersection of the two domains. However, the domain of any polynomial is just a set of real numbers. So let's mark it. df is a set of real numbers, and also dg is the set of all real numbers. Therefore, domain of f plus g is also all real numbers, not a problem here. Similarly, the function g minus f of x is g of x, which is this one. So we can write x squared minus 4, and then we need to subtract f of x, which is that much. So we need to put a bracket, x plus 2. Simplifying, it will be x squared minus x and minus 6. And as before, the domain of g minus f is the intersection of the two domains, which in this case is just all real numbers with no change. The next exercise asks us to find out what's 2 times the product of f times g. So this is 2 times f of x times g of x, which in our case is just multiplication of the two polynomials, x plus 2 and x squared minus 4. We can leave it that way, or we can perform this multiplication and leave it in a third-degree polynomial if we wish. So this multiplication you can perform by yourself as a practice. Now the domain of my new function fg is, as before, the intersection of the two domains, which is still all real numbers. The following example calls for a new function, which is a combination of a product and a difference. So we multiply two f's. F of x is x plus 2 times another f of x plus 2, so that means that we need to square it, and then subtract g of x, which is x squared minus 4, but it has to be in a bracket. So the first one, when you unfold, remember perfect square formula calls for 3 terms, so it's x squared plus double the product for x plus 4 minus x squared and plus 4. That gives us x squared will cancel, and we end up with 4x plus 8. Still, the domain of the new function, composed by f times f minus g, is as before all real numbers, no change. Now the following question calls for producing the quotient function g over f. So we need to take g of x and divide by f of x. Since g of x is x squared minus 4 and f of x is x plus 2, we can think about simplifying this expression, because in the numerator we have difference of squares, which factors into x plus 2 and x minus 2. And the denominator is also x plus 2. So we can actually reduce the x plus 2, leaving us with x minus 2. Now, here's an interesting thing, because when you look at the last resulting expression, this is a polynomial. Therefore, we may think that the domain is all real numbers. However, to calculate domain of g over f, we need to remember to take the intersection of two real numbers, which is still real numbers, but also deduct all the points that will make the denominator 0. So for example, x equals negative 2 can't be really taken for the domain. We have to get rid of it. So the domain of g over f is actually all real numbers except for one particular number, negative 2. As you see, the domain of this expression, which is actually the quotient of the two functions, is not exactly the same as the domain of the resulting expression. Therefore, every time that we simplify expression, we need to keep in mind that these two expressions are equivalent only in the common domain. Common domain means the smaller one, the one that applies to both of these expressions. They are not equivalent in all real numbers though, since this one is defined at negative 2 and that one isn't. So the equivalence is only in all real numbers but not negative 2. And finally, let's consider f divided by g function. So f of x is x plus 2 and g is x squared minus 4, which factors into x plus 2 and x minus 2. As before, we are allowed to reduce, but we have to keep in mind that after the reduction, the resulting expression is equivalent to the original one in the domain of the function f divided by g, which is all real numbers except for the numbers that will make the g function 0. That means this denominator 0. So except for -2 and 2. In the next exercise, we have two functions given. One is a radical one, the other reciprocal of a radical. So let's evaluate the product of the two functions, f times g of 4. That means we need to evaluate what's f of 4 and multiply it by g of 4. So f of 4 means plug it in 4 inside the radical, times g of 4, which is 1 over square root of 4. So altogether we have root of 8, which is 2 root 2, and then divided by root of 4, which is 2. Obviously we can cancel the two 2's, and we end up with just root 2. Next example, f of 0. So f of 0, plug it in 0 here, which is really root 4, minus 2 times g of 9. So we'll look for the g function, 1 over root 9, which is 3. So we have 2 minus 2/3. Altogether, this is like 6/3 minus 2/3, so it's 4/3. Done. The following example calls for f plus g of 0. Well, if I plug it in 0 for f, I'm okay, I can evaluate, that will be 2. However, if I plug in 0 for g, I have 1 over 0, undefined. So, since one of the function is not defined, the 0 actually doesn't belong to the domain of both functions. Therefore, overall, this value is impossible to calculate. This whole thing will be really undefined. And the last example, we need to evaluate f divided by g at the point 2. So f of 2 is root of 2 plus 4 is 6. G of 2 is 1 over root 2. So we can simplify this by changing division into multiplication by reciprocal, which is root 2 over 1. So it's just root 2. And then under the root we really have 12, so we can pull out the 2 and root 3 stays under. Next, in preparation for calculus, it will be very important to be able to calculate a difference quotient, an expression as you see over here, difference in y values over which really represents a slope between two very close points on the curve, on some sort of function f of x. So let's analyze this diagram. If this is our function f of x, and we look at the point on this graph, then this point has coordinates x and f of x. If we go a little bit farther from the x value on the x-axis, let's go by tiny bit. This tiny bit quite often will be called h. So the new point on the x-axis is x plus h. Therefore, the coordinate of a point on the graph will have the input x plus h and the output f of x plus h. So the slope of a secant line that connects these 2 points is the difference in y coordinates over the difference in x coordinates. Since the difference in y coordinates is actually the same as on the diagram on the y-axis, f of x plus h minus f of x. So that's what we have in the numerator of this formula. And then we divide the difference in x coordinates, which really is the same as our h. So x plus h minus x is just h. So this is the formula for difference quotient that represents average rate of change. It tells us how the function is growing over, for example, a period of time h. So again, the difference quotient represents the slope of a secant line connecting 2 points on the graph, and it can be considered as average rate of change, or sometimes called velocity, between the 2 points on the graph. So let's practice how to find difference quotient for various functions. For example, if the function is this linear function, we need to find out f of x plus h minus f of x divided by h and simplify. So what is it? F of x plus h, I need to get f of x plus h, I need to replace the previous input x in my function f by the bracket x plus h. So I have 2 bracket x plus h plus 1. So whatever is written here, it represents only f of x plus h. Now I need to subtract, and because of subtraction, let's open a bracket because something larger is coming in. And then we evaluate f of x, which is just 2x plus 1. Everything is over h. So this part is our f of x, and we have f of x plus h minus f of x divided by h, so yes, that's our difference quotient. Now let's simplify this difference quotient by opening all the brackets, so it's 2x plus 2h plus 1 minus 2x minus 1 over h. The 2x's are gone and the 1's are gone, and then when you end up with 2h over h, the h can also be reduced and we end up with simple 2. So the answer for this difference quotient is 2. Now let's try this function. So the difference quotient, again, start with writing the formula so you remember better. That's what we need to calculate. F of x plus h, instead of x, I replace it by x plus h. So I have 1 over x plus h minus 1 over x, which is just f of x, everything over h. And I end up with a complex fraction. So there's a couple methods of dealing with it. We could, for example, multiply the top and the bottom of the fraction by common denominator of these two small denominators, so by x and x plus h. And here as well by x and x plus h. So overall, if we multiply this by the first fraction, the x plus h will be gone, so we end up with just x. And by the second fraction, the x will be reduced, so we end up with a bracket. But it's very crucial that we actually write this bracket. It may cause lots of mistakes if we don't write the bracket, because in the future we are going to switch the signs when releasing the bracket. So everything is over h, x in the bracket. After simplifying, we have x minus x and minus h. We can reduce the x's, and then after this reduction, we see that the h can be reduced as well, leaving us with -1 because of this negative. So the final answer will be -1 over x and x plus h. And the last exercise, again, we will try to find out the difference quotient. So f of x plus h means that I replace my x's in a formula something square plus something. I replace them by x plus h, the input x plus h. So far, I have just f of x plus h. Now I need to subtract f of x, that means this whole thing. So let's put a bracket, and that will be x squared plus x. Everything over h. And we need to simplify this expression. So perform perfect square formula correctly. X squared plus 2xh plus h squared. Then open brackets. Remember to switch the sign. everything over h. Now we can reduce whatever is possible, for example x squared, negative x with x, and the resulting expression will have a common factor h, so let's take h out of the bracket. This will leave us with 2x plus h and plus 1 over h. Finally, we can reduce the h, and we end up with 2x plus h plus 1. That's the final answer for the difference quotient. So we talk about addition, subtraction, multiplication, and division of functions. Functions can also be composed, and the composition of functions works kind of like riding two taxi cabs. So if the first function f is your first cab, it picks up the blue points and brings to the pink points. Think of those regions as blue station, pink station, and a green station. We pick up a point from the blue station, we leave it in a pink station, and then the second taxi cab, which is called G, picks up pink points and brings them to the green points. So through using these two functions, the blue points can finally reach the green region. And this process can be replaced by a new function, which is called a composition of these two functions. And the composition of function is actually taking a blue point and leaving the answer in the green region directly. So composition of two functions f and g, for example, g composed with f of x, is defined in such a way that f operates first. The function that is written closest to x operates first on x. You end up with the value f of x and then apply the g function to the value f of x. So write with the g function, bring it to the green. Now, this can be done as long as f of x sits actually in the domain of g. That means as long as this f is actually bringing the point into pink region, not somewhere else outside of the pink region, if the pink region is the domain of g. How can we find the domain of the composition of the two functions, g composed with f? Well, the idea is as follows. The domain of the composition of the two functions is the domain of the f function, the inner function, intersected with the domain of the resulting expression. So after calculating g composed with f, we have certain expression, and this expression will have its domain. We always need to cross it with the domain of the inner function as well. Let's see how it works in practice. We need to find the composition f of g of x and the other way around, g of f of x. Remember that the function that is closest to the x operates on x first. So in this case, g operates first. And then also find the domains of each composition, if we know the two given function as indicated here. So let's find out f composed with g of x. What this means? Well, that means that I leave the f for later and I evaluate g of x first. So it's f of, and g of x is whatever I see here. So it's x squared minus 1. The g of x becomes input for the f function. So the input will replace the previous x in the f function. Therefore, we have 2 times the input plus 1. Our input is x squared minus 1, so that will be written here. X squared minus 1. Okay, so let's simplify this. This will be like 2x squared minus 2 plus 1, so it's minus 1. Another quadratic polynomial. What is the domain of f composed with g? Well, let's record it here. Domain of f, all real numbers. Domain of g is also all real numbers. And domain of the resulting expression here, which is this one, is also all real numbers. Therefore, domain of the composition of the two functions is definitely all real numbers. There is no problem here. And now let's try the other composition, g composed with f of x. This time we leave g for later and we apply f to the x first. So g of f of x is the same as 2x plus 1. So that's our input for g function, which takes the input, squares it, and subtracts 1. So input square subtract 1. The input is 2x plus 1, so it will be written here, 2x plus 1. And we can simplify this expression performing perfect square formula. So it's 4x squared plus 4x plus 1 minus 1. That will be it. So this is the final expression. And now what's our domain for g composed with f? Again, the domain of the resulting expression, as before, is all real numbers. The domain of the inner function, which is f of x, is all real numbers. Therefore, the overall domain is also all real numbers. And we have a couple more questions to go through. You may want to stop the video and try those questions by yourself. And if you have any problem or just to check it, you may watch the video later. So let's try f composed with g of x. That's f of g of x is x over x minus 1. And f is taking this as an input and plug it in instead of x. So it will replace this spot. This whole input will be written over here, x over x minus 1. And now we need to simplify this complex fraction. Let's multiply the top and the bottom by x minus 1 in order to cancel this denominator. So we'll have x minus 1 in the numerator, and this times this, the bracket is cancelled, so you end up with just x, plus 1 times the bracket is x minus 1. Overall, x minus 1 over 2x minus 1. That's the composition function. So, what's the domain of the resulting expression? Well, it's all real numbers except for the number that will make this denominator 0, which is 1/2. What is the domain of the inner function, which is in this case g? Well, the g function is this. The domain of g is all real numbers, but not 1. Therefore, the domain of composition f of g is the intersection of these two domains, which mean the smaller one, the one that does not have 1/2 and does not have 1. So all real numbers, but not 1/2 and 1. And if we want to calculate the other composition, g of f of x, then we have g of 1 over x plus 1, which means in every input for g, we plug it in this fraction. So it's 1 over x plus 1 over 1 over x plus 1 minus 1 outside. So we see that this input is actually plugged in these two spots where the previous x and x was. Okay, let's simplify this, for example, by multiplying the top and the bottom by x plus 1. So in the top we have just 1, in the bottom we have 1 minus bracket x plus 1, which means that we have 1 over 1 minus x minus 1. The two ones are gone, so we end up with just negative 1 over x. A lot simpler expression. So now the domain of the resulting expression is all real numbers but not 0. The domain of the inner function, which in this case is f, is all real numbers over here, but not negative 1. Therefore, the domain of the g composed with f is the intersection of these two, which is all real numbers but not 0 and not negative 1. And the last example from this type. Again, let's try to calculate f composed with g of x. f of x squared minus 5. We plug it in x squared minus 5 wherever the x was previously in f. So it's square root of x squared minus 5 that replaces the input, and then plus 5. Since minus 5 cancels the plus 5, we end up with square root of x squared. Okay, but square root of x squared, normally this is absolute value of x. So remember, if we don't know anything about x, this will be absolute value of x. Therefore, the domain of the resulting expression is just all real numbers, because absolute value of x is defined for any real number. The domain of the inner function, which was g, is all real numbers as well, because it was polynomial. So the domain of the composition f composed with g is also all real numbers here. And now let's try the other way around, g composed with f of x. We start with g applied to f of x, which is root of x plus 5. That takes the root of x plus 5, squares it, according to what g says, square the input, and then minus 5. Now, since we square the root, we end up with just x plus 5. So it's x plus 5. We don't have to worry about absolute values, because x plus 5 must have been in the domain of the root if this root existed in the first place. So we don't have to worry here. This is just cancelling the root. And then minus 5. These two 5's will cancel each other, and we end up with single x. Again, domain of the resulting expression is all real numbers, because x is always defined. Domain of the inner function, which is f. Let's calculate this on the side. To find the domain of f, we need to protect the radicand. The radicand, x plus 5, must be bigger equals 0. So x must be bigger equal negative 5. So domain of the f function is from negative 5 up to infinity. Therefore, the domain of the composition function, g composed with f, is the intersection of these two, which in this case means the smaller one, negative 5 to infinity only. Let's make an observation. We calculated both f of g and g of f, and most often we didn't actually get the same answers. For example, in b, one composition was this much, the other composition was totally different, that much. Here we have very similar ones, but still not quite the same, because this is x, this is absolute value of x. So generally, composition of functions are not commutative. You can't interchange the order. Here we have some interesting diagram that may help you to understand the composition of functions. For example, we have 4 numbers, 1, 2, 3, 4, in the domain of the g function in the blue region. Those numbers can travel by g function to go to the yellow region, and since g is doubling the numbers, those numbers becomes 2, 4, 6, 8. So that will be the range of g function, and the range of g function becomes the domain of the following f function, the next one. And the f function is increasing each number by 1, so the function f of x is bringing them to the green region, and the outcome is 3, 5, 7, 9. The overall composition f of g is the trip of those numbers 1 to 3 directly to the green region and leaving the answers 3, 5, 7, 9. So these numbers are in range of f composed with g function. And one more example. Let's say we have these two functions given. Evaluate g composed of f at the particular point negative 2. What does this mean? Well, following the rule, it's g of f of negative 2, which means I apply g to the value f of negative 2. Therefore, I use the f function and plug it in negative 2 instead of the x in f function. So it looks like that. Now evaluate this. That will be g of 4 plus 2, which is g of 6. And now I know what g of 6 is by plugging 6 inside the g function, which is 6 minus 1 in absolute value, so it's really 5. And second example, f composed with g is f of g of negative 2. I take negative 2 and plug it into the g function, so I have absolute value of negative 2 minus 1, which is the same as absolute value of negative 3, so it's actually 3. Now we can follow the f road, and it takes 3 and squares it and subtracts the 3. So it's 9 minus 3, it's 6. As you see, the composition of these two functions at the same point, negative 2, result in different answers. Now let's evaluate the following functions at particular points, reading the information from the given graph. So the blue function is our f function and the red one is g function. We need to evaluate g of f of 1. So it's g of f of 1. How much is f of 1? I start with 1, I go up to f function and I read the value, which is 2. So that's the same as g of 2. But now I go by the red function g and start with 2, evaluate what's the value of g at 2. Well, it's negative 2. So this whole thing is negative 2. Let's try g composed with g. So it's g of negative 1. So we have g, which is red function, at negative 1 is equal to 1. Therefore, we apply g on 1, and at 1, g of 1 is also 1. Next example, f plus g at 2. So we need to evaluate f at 2 and add to g of 2, which is f of 2, f is the blue one, starting from 2, the value is 4. 4 plus g of 2 is negative 2. So 4 plus negative 2 is 2. And here we have a product. Watch that the composition is marked by this little circle at the middle of the line, and the product is either by a small dot or not by anything. If the two functions are written one by the other, there's a product between them. So product really means that I multiply the value f of 0 times g of 0. So f of 0 is 0 and g of 0 is 2. So 0 times 2 is really 0. And another function, this is a quotient. So g of negative 1 divided by f of negative 1. Okay, g of negative 1 is 1. F of negative 1 is negative 2. So altogether negative 1/2. Finally, we have a difference quotient calculated for g function from the point negative 2 to 1, from negative 2 till 1. So at negative 2, the value of the g function is here, and at 1 over there. Therefore, this difference quotient will really tells us the slope of this secant line, how steep it is. Well, judging from the diagram, it looks like the slope is rise over run. So it's 3 over 3. That's supposed to be just 1. Let's see if we get the same number by evaluating the slope. So g of 1 is equal to 1. G of negative 2 is equal to negative 2. And here we have 3. So 3 over 3, yes, it is 1. Slope of the secant line. And last exercise is a word problem, some little application of how to see composition of functions in real life situation. An oil well off the Gulf Coast is leaking, with the leak spreading oil over the water's surface. at any time t in minutes after the beginning of the leak, the radius of the circular oil slick on the surface is given by the function r of t equals 4t feet. Let a of r, which is a function of r, equals pi r squared represent the area of the circle of radius r. Find and interpret composition of a and r of t. Well, a composed with r according to our definition is the same as a of r of t. We want to leave this expression in terms of t only. So, what's r of t? Oh, it's given, it's 4t. So we need to apply area to the input 4t. But then the area formula calls for pi r squared. So it's pi, the input, which is r. In our case, the input is 4t. So pi 4t squared. So the 4t will have to be written in a bracket. Therefore, when we simplify, that becomes 16 pi t squared. And this is already the function of area in respect to time. So how do we interpret it? Well, this formula tells us the area of the oil slick in respect to time. So what is the area when we have given time? In opposed to the previous formula, which gave us the area if we know the radius of the slick. Area in respect to time rather than radius. What is the area of the oil slick after 3 minutes? Well, since time is in minutes, we just simply calculate what a of 3 is. And we can already use this formula. So it's 16 pi times 3 squared, which is 9. 9 times 16, it turns out to be 144 pi. So that's the exact answer for the area in feet square.